Good morning. Thanks for that little interlude for a second. My name is Jenny Disson. I work for the NOAA Cooperative Institute that is part of NC State. Thank you for being part of this morning's session with us. This one is titled Bridging Expertise, a collaborative integration of science, technology, engineering, and climate data domain knowledge. Kind of verbose, but we're hoping to first spend a few minutes describing why we created the session discussion, what we're hoping to get out of it, and have some speakers give you some examples, followed by a group breakout. Okay, but I'd like to acknowledge several folks in the room today. I am part of the NOAA Open Data Dissemination Team. The NOD director, who will be giving a few remarks here in a few minutes, is Adrian Simonson. My colleagues from NC State, Jonathan and Kate, are here. Our cloud partners, Chris and Salar, are both here. So thank you, everyone. It takes a team effort to pull off something like this together. Okay, we have several speakers this morning. I mentioned Adrian Simonson. She's the director of the NOAA Open Data Dissemination Program at NOAA. We have Micah Wengren, who is part of the NOAA IUS team. Jonathan Joyce, who is part of a contracting support staff called RPS Group, which is a Tetra Tech company. And we have Steve Ansari, who's from the NOAA NCEI team, also the NOAA Industry Proving Ground team, and also the NIDIS team. So this morning's speakers are going to cover a couple of things. Adrian will begin by offering some remarks on what does it mean to be cloud ready, and what does that whole concept entail, and why are we discussing this? We are not looking for a solution today. We're looking to have a discussion. So we will be having group breakouts and getting into some key questions where we want your participation and active engagement. Our other speakers will talk about the journey and the transformation and some leading examples, arguably best practices. Let's see, we want to see if you think they're best practices, and use that as a way to show programs and projects at NOAA that have experienced good, bad, and ugly of cloud transformation. And so what does it mean for an organization or a program or line office within NOAA to be cloud ready? So we recognize at ESIP that there are multiple different groups and organizations. While we are providing a NOAA story, we fully appreciate and welcome insights and perspectives from our other partners, agencies, organizations, and solution providers. But, you know, it's ESIP, so we have to have a Slido question. Slido question number 1, please point your phone to the image. It should pull up the question. If it doesn't, you can go to slido.com and put in the code. Question number 1, what do you think is your organization's level of readiness to support operational processing of environmental data from open data sources like the NOD program at NOAA in the cloud? Okay, so let's spend a few minutes. We'll review the responses later on. Give it one more minute. Okay, all of you that have answered, thank you. For those that haven't, we really appreciate you taking the time. We want this perspective as we shape the rest of the discussions. Just out of curiosity, how many in the room have experienced number 4, ready and fully operational today? We've won. Oh, 2, 3. Well, Chris, you don't count. All right. Okay, with that, I'm pleased to introduce you to Adrian Simonson. She is the director of the NOAA Open Data Dissemination Program.
Very kind of you all. Good morning, everyone. I'm so glad you're all here. Really appreciate your time and your input today as well. Cloud readiness is a journey. Where you are in your journey, who you are, and what your use case is impacts your experiences in the cloud. Since 2015, the NOAA Open Data Dissemination Team has had a front row to this reality, as well as the variety of challenges that users experience. We have seen the evolution of cloud readiness from the perspectives of both data providers and data users, as we've navigated the cloud ourselves and helped colleagues and data users navigate it as well. Providing access to NOAA's data via the cloud has had significant implications for a wide range of applications and roles throughout the years. So what makes data cloud ready? From NOAA's perspective as a data disseminator, a level of high cloud readiness entails that the data are easily accessible, well organized, and integrated with cloud-based tools and services. These factors allow users to efficiently analyze and apply the data into their own decision contexts. When the associated data community is ready, we find that it enhances collaboration, scalability, and innovation by providing data and software engineers the agility to process large data sets and near real-time data feeds and perform complex analyses to respond to rapid needs in real time. What we have found is that in the context of readiness, there is no one-size-fits-all. It is an iterative process for both data producers and data consumers. Data producers don't have the means to build the data for all the possible uses of a data set, so they build it for the most possible uses and within a more defined scope. From the data consumer side, data consumers start with what they know and can then leverage learning resources and subject matter expertise to optimize processes over time. Understanding how to work with environmental data and maximizing its use is a valuable skill and one that we can see an industry developing around. So today's conversation is meant to be an ongoing one as we all work together to figure out how to resolve the numerous challenges users face. Thank you.
Thank you, Adrian, for that description and essentially a problem statement that we will be referring to multiple times throughout the session. So the next three presentations are an example of NOAA's journey across a couple of the programs. So with that, I'd like to invite our first speaker, Micah Wengren, who is from the NOAA Integrated Ocean Observing System. Micah, take it away. I will flip the slides for you if you like.
Okay, great. Thank you, Jenny. And thanks everyone from the organizing team for including me. Next slide, please. As Jenny mentioned, I'm from the U.S. IUCE program, which is part of the National Ocean Service, and I'm the system architect there, managing our data and cyber infrastructure. So a little bit of background about IUCE. For those who aren't familiar, IUCE is a cooperative, coordinated network of federal and non-federal ocean observing networks that's been in operation since 2009. So IUCE is made up of 11 different RAs, regional associations throughout the country who are responsible for their specific geographic areas of the ocean for observing and monitoring. So these independent partners of IUCE, part of the IUCE enterprise, are responsible for actually deploying the observing systems, measuring the ocean, handling the data, and they actually go through a certification process that effectively blesses the data, certifies the data that they produce as being essentially NOAA data. So both for the purposes of all of the data management policies that NOAA abides by, the data that's produced by IUCE's regional associations is essentially no different. So on this slide, the data at the bottom you can see is the main purpose is, of course, to support ocean weather forecasting, maritime safety, and ocean and public health, and including things like forcing oceanographic forecast models on the lower right. So the point here is that these 11 regional associations operate their own independent data management systems. So although they're producing NOAA certified data, they're each operating their own IT systems in ways that are appropriate for their regional and stakeholder priorities. So next slide, please. So this gives an overview of what a generic regional association data center consists of. So um, on the left, we have the inputs, which are essentially the observing platforms, anything from moored buoys in the ocean. We have profiling autonomous gliders that move throughout the ocean and water column to take more dynamic measurements. We also operate a surface current or HF radar network, as well as some other sensor platforms, including animal telemetry network. As well, the RAs operate their own oceanographic forecast models for their particular region of interest, and those data are also fed into these RA-operated data management systems, as well as a variety of biological observations that are also managed similarly. So on the left of the blue box in the middle, you can see the purpose of the DMAC program is to establish a set of common standards that these RAs use when managing these data. So it can be anything from the data formats that are used to capture the data, such as NetCDF in the case of a lot of the physical observations or forecast data sets, to CSV or Excel spreadsheet formats for more commonly used in the biological observation space. And so on top of these underlying data formats, there are community data standards that are applied, such as NetCDF CF convention, Darwin Core, et cetera, to make the data interoperable by IUS's user base. And then the data are then, once collected by the RAs, they're served through a array of standard services, such as the Threads or ERDAP servers, from which users can then access the data through a suite of standard web service formats. So there's a few listed here. Data users, of course, on the right. And additionally, there's also an aggregation process that happens, allowing the data to be aggregated at the national scale from IUS's 11 regional associations. And we actually manage a suite of national DMAC products, such as the IUS Model Viewer or Environmental Sensor Map, that display a full-scale enterprise picture of IUS's data and also make them available at that scale for national scale users. So next slide, please. Thank you. So what I wanted to focus on for the time that I have is, so the previous slide was essentially representing the current status quo of the DMAC system, namely that there are 11 independent entities that each operate their own data management system following these principles, which gives certain advantages. There's obviously flexibility there. The RAs can tailor their solutions according to regional stakeholder needs and priorities. They have full control over the systems in terms of where they're operated. But it also creates some redundancy. So obviously, where there are advantages in having that flexibility, it doesn't always make the most efficient overall system to be doing the same thing 11 times, give or take a few. So this slide here is a depiction of what a hypothetical cloud-centric DMAC data system might look like. So you'll recognize the data are coming in on the left. The box in the center is what we might call the DMAC National Cloud environment. So this is an alternative approach that is a potential solution. We don't have this currently, but it's something that we're interested in pursuing. And I think it's very relevant for the session today. Essentially, what this might consist of is a centralized cloud-based object store where the equivalent of the full aggregate um, content of the IU's data system might be stored again in some of the similar data format standards, but leveraging object storage on a cloud service provider. So if you look on the upper right of the slide here, we have our data users again. They're still able to access the data in the traditional ways that they're used to. The RAs, represented by the smaller blue boxes, are still operating the same standard services that we recommend or require today. However, what this opens up is the possibility for a secondary type of use of the data. So what is commonly labeled data proximate computing. And if you look inside the blue box in the middle, the data users there are depicted a little bit differently. Don't think of them as very different from the traditional data users, but when I was trying to make this slide, the best I could do to represent this this different profile of user is shown here, but they're not just inverted for no apparent reason. Think of them as doing data proximate computing cartwheels. So they're actually bringing their analyses to the cloud environment adjacent to the data and accessing it through the an object storage API such as S3 or Google Cloud Storage, to name a few. But they're sort of the more advanced, or kind of without a better way to describe them, the sort of novel new type of user that's more comfortable with actually doing compute in a cloud environment, and also has access to resources in order to do that, whether it be Jupyter Hub, um, uh, other tools like this that allow you to kind of do more programmatic interaction with the data rather than downloading it to your computer to do local analyses, which the more traditional data users in the upper right might be doing. I wasn't able to, change the logos, so that's the best I could do, and this to represent that sort of shift in terms of the user profile. But all this is to say that this opens up the opportunity for greater flexibility in many ways, because the regional associations, if we were to create an architecture like this, might be able to migrate some of their own services onto the cloud platform adjacent to the data. So that's represented by the box in the middle. So some RAs might choose perhaps to run their services directly on the cloud provider adjacent to the data. Others may not, however. So we have to account for that scenario in our prototype architecture design as well. So on the lower right of the slide, you can see some may actually choose to operate certain services outside of the cloud, and which is perfectly fine. However, the important point here is that the egress of the data from the cloud is a critical piece here. So I think this is something that is essential to consider. And in NOAA, we have what's a great program actually that helps us to overcome this challenge, which is NOD. And that service, that agreement that NOAA has with the cloud providers, essentially solves the data egress problem, because any data that's posted to NOD is able to be accessed by external users without incurring data egress fees. So that's a really critical piece, and I think something that is especially important for us to consider as we, IUCE and other open data providers, migrate to a cloud architecture. There are there are challenges with adopting cloud for open data providers, primarily in the data egress area, because if you essentially require your users to um, migrate to the cloud in order to access your data, you could argue that it's not actually open data in the traditional definition of the term. So I think it's important to have this flexibility and to have, to plan for how you're actually going to serve users that aren't comfortable with moving their workflows, or perhaps don't have the resources to set up a cloud account, or otherwise are unable to do this transition and move to a more cloud-centric approach. So Nod is one example of a way to solve that. I've listed another one here, Open Storage Network, which I think some may be familiar with, but there are other providers as well that could go on this list. And I think this is something that IUSE are thinking about, and any other open data provider, I think is really critical to think about how to address the data egress challenge. So thank you. I know I'm short on time here, but I did want to mention and just give a lead in a little bit to the next presentation. But IUSE recently put out a funding announcement to try to work towards this goal outlined in the previous slide of innovating the DMAC program. And some of the main goals that we had in this funding announcement that is just wrapping up now was how to incorporate cloud better, how to improve the overall system efficiency of the DMAC system and reduce costs. So we're really thinking about ways to kind of trim the fat and to optimize. And as a result of this funding proposal, one of the projects that was funded was called Reaching for the Cloud, which was carried out by RPS Group. And I think I'm going to close there and pass it off to Jonathan, and he'll give you some more details about that. So thanks very much.
Thank you, Micah, and passing back to you, Jonathan. Take it away.
All right, thank you, and thank you, ESIP, for having me, giving me this opportunity to present. Like Micah mentioned, we're with RPS Group, and we're kind of the technical side of IUSE through cooperative agreements, and so we're a collection of cloud architects, software engineers, really working toward seeing and testing out what these new cloud-based systems would look like for IUSE. So next slide, please. So like Micah mentioned, the Reaching for Clouds project, this is a project we've been working on over the last 3 years, and we've mainly been developing a number of prototypes to prove out these different ideas. But before we got there, right, we had to kind of reimagine how IUSE data management would look in a cloud native environment, and then also identify the tools and technologies that would get us there. As well, like a lot of the existing systems within IUSE, they were developed a long time ago before the cloud existed, and so they aren't able to make use of some of the new paradigms that make it cost effective or even efficient to serve data throughout from the cloud. As well, we wanted to take new ideas that have developed, like from the analytics community, emerging in AI and data science, and as well connect with the existing open source communities, which have only continued to grow and serve this community. Next slide. So I think most people are probably familiar with like some of the things that are different about the cloud, and these are things, right, that have kind of driven our design, as in coming from like operating on a single machine or a single server. The big difference with the cloud is that you're able to kind of generate resources on demand, right? And then the longer, though, that you keep a lot of resources around, the more it costs. So you want to really be able to turn machines on and off when you're not using them. The other one that we've talked a lot about, object storage, but this is not the same as accessing data from a hard drive or a network file system. It's really built to be scalable and reduce the total cost of storage. But as far as requesting data, you want to split out those requests into many smaller requests. And so that combined with compute, many smaller machines, grabbing smaller chunks of data is really the more optimal way to work in the cloud. As well, this isn't really a cloud feature, but you have the ability within a specific cloud environment to do more event-driven data workflows. Whereas a lot of the infrastructure now with iUse, right, it's connected through FTP or different file servers where you need to download the data, but you aren't given notifications necessarily when that data is changed or updated or gets filled in if it was late. The other important piece is to think about, right, the total cost of ownership. And with a lot of the costs of the cloud built into that, as well as all the infrastructure management and what you would need to, have to run your services with a team. And so although things like, Lambda can be expensive if you compare it, like if you're going to run it 24/7, which you shouldn't, you do get the benefit of your software engineers don't have to spend as much time managing the machines, the operating system, and the patching, the network, etc., because that's all done in this cloud environment, and you have the ability to also run in different regions. The other point with so then specifically looking at geoscience data in the cloud, the main point is that data structure matters. So there's various file formats, like ZAR is for highly dimensional, like forecast model output. And then we're also able to create indexes into that data regardless of file structure. So typically we've been operating it as in, well, we have either hourly files or daily or something in between, but we're through the ZAR and Kerchunk type things, we're able to create indexes across these and look at it either as a full forecast model output or as like a best time series for the entire run of the model. And then we differentiate that from how we would want to operate with like time series data, say for instance, data coming off a buoy, point observations. You might want to structure your data differently with something like Parquet. And then there's a variety of database engines in front that can operate on that. As Micah mentioned, you want to avoid egress costs, use programs such as Nod when you can. And the other big point I wanted to bring up is a reason to do all this. Also, as geoscience data, should be used to, train more machine learning models. One of the big impediments to using it really is that the existing data structures and outputs are not effective to grab large sets of the data. So a lot of like climate-driven AI, energy systems are also looking at advancing how we structure our data so that they can train a model, with years of data. Next slide, please. So we've developed as part of our prototype system. It's like I mentioned, generating ZAR data. This workflow, I don't have a ton of time to go into it, but essentially we've developed a workflow where when new NetCDF data is added to a certain Nod bucket, we listen to those notifications and then we generate these Kerchunk files, which are essentially chunked references to the existing data. So this makes it so that this essentially makes the data access faster and gives you that chunking capability without having to completely reformat the data. And we are actively pushing those to that bucket below that's publicly accessible, thanks to our partnership with Nod, who essentially are allowing us to serve this cloud optimized data. Next slide. And so what does that get you? One of our other, so other than the Kerchunk piece, on top of that, then we're looking at layered services. And this is a Gulf of Mexico forecast system. This is an unstructured grid with about 500,000 elements. And what we have with the existing solutions, existing services from Threads, is the data has to be regridded. And it's also still not exceptionally performant. A lot of these requests timed out, so we just said maybe it takes 60 seconds. Whereas our prototype with XPublish, it's not even optimized or scaled out, I'll say. We can still make this time better, but we are able to pull from the native grid in a fraction of the amount of time from Threads. In addition, I mean, you can just see the resolution difference. And so, a lot of work goes into, modeling generating these models with a high level of detail. And if our downstream systems aren't able to preserve that information and get that down to the user, then, we've just done a lot of work for nothing. So hopefully you can see the visual difference here and imagine, right, how that might impact your analyses. Next slide, please. And so we've applied this concept to a lot of different projects. And so this is a really exciting time that we've developed this prototype, and now through these different models, right, we're making Kerchunked versions available, which we've done for the National Water Model and the NOAA Coastal Ocean Reanalysis data sets. Our Oceans Map product, which is a map visualization, we're replacing the backend with that XPublish service, whereas before it does work against Threads, and it's a little bit slow. So we're updating that for co-ops, and then we're also providing services to work with the data. So we have a subsetting project where you're able to make an API call or go to a website, your choice, and essentially pull a subset of the data rather than download gigabytes of data of a model, download a few hundred megabytes of just the region that you want. Next slide. So we've definitely, and then so even more examples. I don't have time to go through all of them, but essentially we're following this pattern, and we found it useful to kind of follow the pattern of cloud optimize the data, put services on top of it to make it efficient and fast, and then consumers don't need to be as concerned with the plumbing and the scalability, and then the engineers, like us at RPS, can put all that together. And yeah, I think that's all for my piece.
Thank you, Jonathan. That was great. As we transition to our next speaker, I just want to go back one slide and just again look at the number of examples of projects that we are seeing, or at least they are seeing and working on in NOAA on the ocean side. And I think a lot of this is referencing the importance of cloud access to NOAA environmental data. So that's a major highlight and takeaway that I'm already seeing just listening to what you shared, Jonathan. These examples are great. Thank you.
Yeah, thank you.
I can see that it's non-trivial in terms of looking at different formats and different access and Kerchunking and NetCDF and so on and so forth. But there are a number of different examples here that I hope we will talk more about later. Just real quick, as I get Steve and Sari, our next speaker, to walk on up here, I want to highlight this particular case study here on Nod and Camus Energy. Camus Energy and Adrian Simonson were both on a... Yeah. Thanks. Adrian Simonson gave a talk at a webinar called ESIG, Energy Systems Integration Information Grid, where Camus Energy invited the Nod team and Adrian to talk about NOAA data accessible via the cloud that allowed them to develop cloud-based load forecasting for the energy industry. So that's a really interesting case study. For anyone that's interested in that, please come and talk to us. All right. Our next speaker is yet another example of how NOAA data via the cloud has enabled development in drought monitoring. So with that, I pass it over to Stephen. Sorry, take it. Okay, this is the button for moving slides.
Thanks, Jenny. All right, so yeah, I don't quite have the exclamation point thing going on my face. All right, well, thank you for having me here today, and I'm going to talk about how we have been using NOD resources and data to support drought.gov over the last 5 years. I'm going to talk about how we plan to use NOD in similar fashion to support the Industry Proving Ground project. And I realized sitting there, I could have put maybe some more slides together. So I'm just going to go off slide and give a little history here about watching Adrian talk and Jenny talk and the folks talk about how they're using NOD. I have really had the privilege of being involved in this program from its inception as the Big Data Project. And I was looking at my email. How long ago was that? And it was 9 years ago this summer that we first worked together to get all of the Nexrad level 2 data off of the NCEI tape archive and into Amazon Cloud Storage as part of the NODD project. And I was really fortunate to be a part of that. We put those robotic units, they were smoking at the 3rd floor over in NCEI there. Every spare moment we were dumping data, pulling it up and pushing it into Amazon. And it was a tremendous success story in what we saw in the subsequent years at conferences like AMS, where you would see folks using Nexrad data and doing new things with it that never could have been possible before. And it's just awesome to see that, right? Like, that's why we're all here. And NOD has really been a huge part of that. I don't know if there's really been much I've been a part of at NCEI in the last 10 years that have, to me, felt like it's moved the needle that far forward for science with our data. So I'm excited to talk about the other ways that we are using it now beyond Nexrad, even though Nexrad's always at the core of my heart. I love radar stuff. It's really, really fun. So open, unauthenticated cloud-based access. That's really the magic of what NODD is all about, right? Is that the contract and the agreements with the cloud service providers have developed this business model where everybody wins. And that's awesome, right? Because the cloud service providers are winning, otherwise they wouldn't be doing this, right? So they're getting something out of it. Humanity is getting something out of it because we can have access, open access to all of these files and do stuff with it and start doing science with it. We can move data from Amazon into Google to Microsoft to open container-based platforms we have on premises, whatever we want to do with it, without having to have egress fees, without having to authenticate and manage user profiles and user access stuff. It's that easy. The other side of it is this Nexrad data bucket that we have out there. And I know model data might be another example of that. If I want radar data from NOAA, I shouldn't need to know our organizational structure, right? That real-time data, I go here, historical data, I go here, forecast data, I go here, and I have to download it from 3 different file servers that are out there. That's how it used to be. That's not how it is anymore. There's one bucket where the real-time data goes and the historical data goes. It's all in one place. That simple sort of data usability trick, I think, has really made a huge difference in how people interact with the NOAA data out there. And again, NOD has really facilitated that. In drought.gov, we have focused the last 5 years on making our websites and tools data-driven, that have interactive features to them that include interactive mapping, include statistics and graphing, all of the data that we're using on drought.gov, if you go there right now, is coming from Nod. We're using cloud-ready formats, web-ready formats, and we're using Nod storage to drive the drought.gov site. And it's allowed us to totally rethink and change how we're doing stuff on that site. And without getting too deep into like what technology we're not using and what we are using now, the goal of it was to allow us to scale and allow us to reduce our future O&M costs, our operations and maintenance costs, to make things simpler. And as many of us working in the cloud environments have seen, that's one of the advantages you can have in working in the cloud. Things can actually get simpler. So what we're focused on, again, are cloud optimized formats. We're using a lot of data in the cloud optimized GeoTIFF format, mainly because a lot of our stakeholders and users in the drought community and people that want to take our data and do additional things with it, like incorporate into their own models, into their own decision-making processes, use GIS tools. It's just how it is. GIS is prevalent across many different sectors and many different user groups out there. And cloud optimized GeoTIFF is a format that works just fine on your desktop GIS and also allows you to do some really fancy cloud access stuff as well. We're also using tools, platforms that NOAA has contracts with that allow us to do rapid cloud-based development. Private sector tools of ArcGIS Online from Esri and Google Earth Engine, which we this year have a new contract with that allows NOAA-wide access to that tool. Our general architecture, the way that we're doing this is we're using Nod for the storage of the cloud-ready formats. And then we are using the platforms of ArcGIS Online and Google Earth Engine to read the data from the Nod storage into the platforms to do analysis. What this means is that we are working on, we're working on ways to, right now, get the data into ArcGIS Online and have it point back to the data that's sitting on Nod storage through technology they call like a raster proxy. It's this kind of new stuff on the Esri ArcGIS Online. We don't have it quite worked out yet, but we're almost there. That would allow somebody making content in the Esri environment, like a story map that wants to visualize some gridded data that we have on Nod storage. That story map will be hitting Nod storage behind the scenes to do that. And so what does that do? It reduces potentially the cost of our storage in the Esri cloud environment because we're reusing the Nod architecture and storage contract for that. Same thing with Google Earth Engine. Google Earth Engine can natively read cloud optimized GeoTIFFs that are sitting on Google Cloud Storage, which is part of Nod. So we're putting our cloud optimized GeoTIFFs there that allows Earth Engine to read the data and do the analysis, but also allows anybody to download those cloud optimized GeoTIFFs for their own GIS analysis in an open, unauthenticated way with no egress fees. By having data in Nod, now we're part of a bigger pool, right? A bigger lake of data that includes data from not just NOAA. And so now, while Nod is a NOAA program, Nod has allowed us to elevate our data into the data lake that includes data from other federal providers and other free data programs that exist at Amazon and Google and Microsoft. So that when somebody designs an algorithm that does some sort of NDVI analysis or does a precipitation analysis, we can apply it to data not just within NOAA. We can scale that algorithm out and basically plug and play it in to work with data from ECMWF or from NASA or USGS data. So now we can focus on the algorithm and not on writing sort of stovepipe code for one data set and then having to replicate that and reproduce it and then maintain it for multiple data sets that we want to run that on. So why does this matter? The whole point of this for us is from a user standpoint, moving towards being able to provide answers. And so in addition to how awesome it is to download the files from Nod, we also want the users to be able to use tools out there that they don't have to worry about what the files are. They're working with the collections and answering questions from the entire collection to get an answer, and can do it in real time. So this is an example of if you wanted a map where you wanted to see what the most severe drought category was over the last 10 years, we could generate that in real time with tools that use, in this case, Google Earth Engine and a tool called Climate Engine that sits on top of it. So that's the end of my slides today. But again, thank you for having me, Nod, and great stuff.
Okay, thank you, Steve, and thank you to Jonathan and Micah again. So for those of you in the audience, you have heard examples of NOAA case studies and NOAA journeys on using environmental data via the cloud. Now we'd like to hear from you. And before we get into our group breakout, we've got 2 more Slido questions. So pull up your phone, we're gonna go to Slido, and we first want to understand question number 2. What are some of your biggest obstacles that you or your organization are facing as you are starting to think about transitioning to cloud-based data solutions? This is a multiple selection. You can choose all, you can choose none. Slido.com, there's a code number. Take a couple of minutes. How many of you suspect that most people will select all? But for those of you online, please do log in to slido.com. Okay, another 30 seconds. Okay, all right. And we're not done yet. We've got one more. The responses to these questions we will review after the breakout. Okay. Question number 3. What do you perceive are the main barriers in using NOAA data via the cloud? I know we have colleagues in the room here from other agencies, NASA, USGS. I guess part of us looking at environmental data, we're a little bit interested in the NOAA data, but in the group breakout, would really like to hear from your perspective on what you think could be the main barriers for other agencies and other groups. This question, we're a little bit interested in the NOAA side. I think you can select more than one here too. I think several of you will be selecting all. Okay. Okay. So thank you for taking the time for responding to the Slido questions. They're really, really helpful. We don't often get a chance to be in a room with data experts or data engineers or software engineers and cloud experts. So for those that have a little bit more experience, we want to understand how we can continue to build upon this cloud transition. NOAA data is unique and special, given that it comes in a lot of unique and special formats. Cloud users really want it in cloud optimized formats. So there's a big conversation there to be had. So let's have that conversation. We are going to now get into our group breakout. I'd like to invite my colleague Kate here to stand up. We will have 2 groups, group 1 on the side, group 2 on the side. Group 1 is with me. Group 2 is over here. If you're sitting on this side of the room, we'd like for you to be part of group 1. If you're sitting on that side of the room, we'd like for you to be part of group 2. Yes, we're going to make you all move a little bit. Sorry. Yes, we are going to stretch before lunch. Engagement involves interaction. Interaction sometimes means making you move. Thank you for indulging us. In your groups, you will be tackling 4 questions. Okay. I will keep track of time for 4 questions. Yep, I'm good. Okay. For participants online, we ask you to please look at the questions and drop your comments and reactions in the chat. For those of you in the room, we're seeing a little bit of chaos, which is exactly what I expected. We want to have a little shuffle, gonna move folks around and get people to talk. This is great. All right, group number 2. You are with Kate. Kate will be your guide. Group number 1. I will be there in just a second. Yeah, I'm group number 1. I'm coming over there. Kate's group number 2. She's over here. Okay, all right, we're getting ready for our first question. And this is a discussion. Breakout question number 1. Okay, how do you think computer scientists or engineers can work with environmental experts, environmental scientists, environmental data experts to improve data readiness? The reason we're asking this question is we want to understand what and how can functions like user engagement help develop methods to integrate perspectives from the computing side of things with those that are domain experts, those that are PIs and scientists. It's a big question. So I'm going to go over to my group and you have about 5 or 6 minutes. Have a good time. Can we, excuse me, we need to can you hit refresh? Like, we want to pull the presentation up again. Because she has notes. Can you just pull up the, yeah.
Which one was that?
Nod. Yeah.
This one?
Yeah.
No, that's PowerPoint. We're in the Google slide, the one above it. Sorry.
This one?
Yeah. Okay. All right.
Yeah.
Oops, question, you have summary number 2. Okay, all right, thank you.
Very detailed, so I said we'd summarize it later.
Thank you all for taking the time, for giving some really productive and insightful comments. In the remaining 7 minutes, can I bring you all back together? You may stay wherever you like. For those of you online, first of all, I want to acknowledge and thank you for participating virtually in the responses to the questions. In the remaining few minutes, I want to do a couple of quick things. 1, we have had a very productive group breakout discussion, and the number of notes and comments are pretty extensive and pretty helpful. Sadly, we don't have time to review all of those. So we encourage you to please look at the document that is associated with the session. That is where Kate and I will be typing in all of the comments and the things we heard. However, we do want to touch upon a couple of them really fast. And Aesop likes to do popcorn. Are you familiar with the popcorn style of comments? where if one person makes a comment and if you agree, you just raise your hand. Okay, so I was part of group 1. I'm interested in group 2 takeaways. Kate has been able to type this in faster. I wrote it good old-fashioned way on my notepad. Okay, so for the first question, any one particular person want to jump in with a reaction or response to the first question? Okay, remember who remembers the first question?
Yes, I agree, because I said a lot.
Okay, okay.
Is
The
that what you wanted? I'm not quite sure.
Yeah. So question number 1. Was how can computer scientists work better with basically domain experts or scientists? The comment we heard, which we like a lot, is researchers are curious on who is using the data, how it's being used, and that computer scientists and engineers can help facilitate response to that question. Okay, that was 1. Who agrees? Okay, we've seen versions and variations of that already happening, and the NOAA team has been able to kind of move forward a little bit in that space. We never really get to know who exactly or specifically is the user, given some of the rules and regulations for privacy, but we can get enough insight to then have targeted other engagements to discover who the other users are. Okay, all right. Question 2, 1 comment. Do you remember this one where we talked about workflows? It was technical. What are the challenges you're experiencing migrating workflows? Okay, anyone particular want to jump in with a comment? We had one in group 1 over there. Rich said web services don't need to go away. Okay, there's many other comments that I think I would like to share. Yes, Adrian, jump in. Oh, agree. Okay, web services don't need to go away. Okay, all right. All right, this was the fun one. Okay, gonna look to the side over here. Unlimited resources. What one solution would you develop or invest in? Oh, okay, we didn't have that one. Well, agree. Okay. Okay. We have a number of comments online and we have a couple more minutes. So where do I pull up my comments? Okay, going online for a second. Okay, where am I going down further? Question 3. Okay, let's talk about question 3. Assume that there are unlimited resources. One comment, and I will read this out loud. My view is that NOAA and other open data providers should continue to provide free and open access to all data, whether on cloud or not. I think we heard that as well. All data on object storage, all the time, within seconds. That's what we heard. I am interested in egress-free object storage solutions. We heard that. Including not how to ensure programs like this are fundamental. To have federal agencies adopt commercial cloud. Budgets are a challenge, yes. Here's a question. Have any other agencies or data providers investigated similar solutions? Or object storage service that aren't behind CSP egress paywalls? My USGS colleagues in the room, NASA? Yes, DevSeed. Okay. Okay. In my remaining 2 minutes, I want to encourage you to please look at the note document so that you can get a summary readout of some of the responses to these questions. I think for my international colleagues here from Met Office and ECMWF, I think these are some of the similar questions that you might be thinking about. And here you get one perspective with participants here from the US. For my solution providers in the room, the Dave Jones and others that are sort of being in this broker role, intermediary, thank you. You are included and at the table, and we need to think of another way to get more intermediaries and solution providers in the conversation. So that's also DevSeed and others. For my government data providers, producers, there's a lot to think about. One interesting comment that I'm taking away is kind of, I sit with the scientists, I spend a lot of time with the NOAA team, but to think about them as a targeted and separate category of users because their needs and applications are unique and special. That's a big one. Industry users are a different bucket. And I think what I'm hearing is that we might be able to lump science and academia in a similar bucket. Let's see. So these are the kinds of things that the NOAA engagement team, the NOAA open data engagement team will be looking at and starting to kind of determine which one of these questions can we start to tackle as part of the NOAA open data engagement efforts. Okay, thank you so very much. For those of you online, thank you so very much for participating. Your comments are being captured. Again, all of this will be summarized in the Word document that ESIF makes available. All right, onwards to being more ready to cloud. Have a good lunch.